eject do? What we have is a restricted access entry system. It's an infrared remote control, just like the one you have at home for your TV or VCR. Same principle. Here we have an infrared receiver. What it does is that when the remote is activated, the receiver picks up the signal. Will either open a gateway, as we've demonstrated here with a car, or a doorway, like a sliding door that you might have in your house or office building. Now when you pass the receiver, the door closes behind you. When the receiver picks it up, not only does it open the door and close it behind you, but we also get a log identifying who you are, whether you came in or out, and the time and the date of when you either entered or exited.
Very interesting.
Yes, I can try to give you a short version of it.
That's cool.
But
so how did you guys come up with this idea?
We took it from you guys.
Really?
Yeah. We overheard you all talking and we kind of like wrote it up and got it in pictures.
Tanya, tell me about your project.
It's an underground line computer. As you detect the line, signal strength gets really strong, you know you're right over it, then you push a button and it plots a point on the computer, and then you go along, you detect it again, you hit another point, and it draws a line from that point to this point, therefore it draws the line as you find it on a computer.
So is that what the posts are for?
Yeah, just, you know, it's just
And who's working in your team?
Marshall Chain and Brent Hirsch.
You guys give me a quick demonstration?
Quick.
Okay. Is that the mechanism, Marshall?
This is actually the locator part.
This is the locator, XY coordinator.
The sensor picks up the 10K signal, which is the source sensor. It's located in that little shaft there. It's basically a little wire. The sense is near the EMF field generated by the 10K signal. The field lines get across it, giving us a voltage. So that is sent through op amps, amplified, and then sent through the comparators. Or a summer, basically, the reference voltage, which will then give us air voltages, high or low. Like farther away, it's not as bright, it's getting closer to it.
Okay.
So that's that part of it.
There's our first point.
Okay.
Zoom in. Come on, zoom in on this.
I'm zoomed
Right
in.
here.
Like Marshall said.
He's okay.
And then we'll do our second. There's a second.
What is it that it's actually doing right now?
It's plotting your underground line.
Okay.
So then you can take a hard copy back with you to the office, you know, you're trying to figure out how you're going to dig up or where you're going to dig up and lay your new lines. It's okay. Hold the locator forward.
That way you have a map of your line.
Okay, okay.
You can give it to your surveyor.
And where did this idea come from?
This came from my dad. He's an underground contractor. He fixes underground cables and stuff like that.
He uses a lot of line locations.
Yeah.
Cool.
Remove a certain wafer people inspection microscope. The way we have it set up, to demonstrate with 5 wafers. Boats hold 25 wafers, we're just doing 5 to show the theory of operation of the system. How it works is that a user will come in, control panel on the front, when power is applied, and select which wafers they want to look at underneath the microscope, which we do not have here. Once those are selected, the boat will move up and down depending on where it is located. So using threshold feedback sensing to each wafer has an address, and so it will locate it in the correct position. Once it's in the correct position, it will stop moving, and the paddle will come in, go all the way in as far as it can go. Then the elevator will move down a small amount to take the pressure off of the wafer in here and put the pressure on here, and the paddle will withdraw from the boat and the paddle, and the wafer will stick on it. That's what we have designed by friction. We'll stay on the paddle, pull out so you can look at it underneath the microscope.
Cool.
Check for problems with the etching, things like that.
You want to introduce yourselves?
This is Wayne Wallenstein. I'm trying to use our great, our public speaking. Larry Miller, Pat Richard, over here.
And
That's Larry's sister,
That's Larry's sister?
Vanessa.
Larry, what are you working on?
I am hooking up a switch to simulate the pick. This will control elevator movement and paddle movement.
So we can simulate it.
The wallet. The wallet is
It's
for
enticement.
incentives to the judges. It's adding weight onto the paddle. It just takes the vibrations off the wafers.
Is there anything that you can show me now? Yeah. Can you turn it on?
Well, you can.
For the most part?
Don't like it.
Go ahead. Well, as you can see, it's moving up and down.
I don't know why it's moving.
Anyway, if you want to look at the control panel,
Okay.
did you take the power up in here? Turn it on yourself. Oh. See, you're supposed to be doing it. You can pick different wafers. We don't have them labeled 1 through 5, for example. Then you hit the start button. Hit the start button, and that's when the process begins. That's when the elevator will lower.
Okay.
Once it's pulled out, then you hit the continue button, which is that one, and it will put the wafer back in and go to the next one.
Where did you guys come up with this idea?
With the idea, we wanted to display something that has a little bit of mechanical nature, as well as be self-contained, self-standing, so you wouldn't have to hook it up to your personal computer. We're using a microcontroller to be the brain of the unit.
You guys gonna be all ready to go by this afternoon?
Oh yeah, 10 minutes.
Location of the 10 by 10 test area grid, which we have here. The destination spot will be represented with a red square, while obstacle will be represented with a gray square. The way we are detecting the obstacles is through ultrasonic detection. We have an ultrasonic sensor detecting the obstacles with a stepper motor underneath going in a 7.5 degree increments to rotate the sensor from an angle of 0 to 180 degrees. Basically, the ultrasonic will sense 0, right in front, right, left, and front. So basically, also it'll sense within 1 foot in front of the object. If it detects anything, it'll send a pulse back to the computer, and then the software will put a gray square on the screen. If there's a square in front of it that's doing running, we're going to ask you which coordinates you want to put in. Put in X and Y coordinates. Let's say it's based destination coordinates. Let's go 3, 3. It's the car, it's the target. If there's any object in the way, you'll see a gray square up here. Look over the stepper motor, it should be spinning around the ultrasonic. Here, I'll block it. Wait for the log. See a gray square up here. Go, square here on the screen. It's a process. Keeps on scanning, checking. Just moving. Just moving. The batteries.
You guys want to introduce yourselves?
My name's Dathan Valdez. I'm Nathan Salska. Christian Muller. Mark Medella.
And what was the inspiration for this project, guys?
One Love. Science.
Why don't you guys introduce yourselves?
Hi, my name is Jason Ryberg.
Michelle can't talk. That's Michelle McLeay.
No,
Where's Russ? Kick over here.
I work for the IRS.
Where'd Hunchy go? Did Hunchy leave? Is he here?
Munchie's over here behind you.
There it is.
No cameras.
Oh, no cameras. All right, well, who's gonna talk?
I've been talking. That's right. You've been practicing.
Somebody talk. You're gonna have to go over more.
Okay, what we've got here is
All
a
right,
personal
thanks.
monitoring system, and if you see Russ, my slave here, walk down there, you'll see that it'll show up here on the screen, and the screen will show the time in, the last hit.
I'm the slave driver.
You just gotta give it a second.
Okay.
Russ
there
and
it is.
Guard, time in, time out, and obviously it's military time, and then there's Hanchi, and you'll see Michelle here in just a minute. This keeps track of their time for maybe payroll purposes. It could also keep track of maybe environmental purposes. It might be able to turn off the lights in the room if that's what it needs to save power. Also maybe emergencies. If you know who's in the room, you know if it has to be evacuated, you know who should be in the room.
Okay.
So if you can't find them, you know what room they would be in. And these badges work at 310 megahertz. This is the transmitter and the PIC and then a 9-volt power supply. We're using time division multiplexing. Each badge transmits for 2 seconds their each individual code, and so for 4 badges it's an 8-second cycle, and each badge transmits in a 2-second increment. And that's
What was the inspiration for this project?
Timmy on Howard Stern. To save the company's money and some safety. It'll save them money like accounting. The computer will automatically get the payroll. The computer can do all that. Safety, it'll save. It might save a life. You know, if they know that person's in there sooner than normal. And again, it can save money by turning off the lights and saving power.
What's this running right here? Is this like a demonstration program?
Yeah, this is PowerPoint, and we're just showing different screens and the different aspects of the project.
Cool.
But right here, this next slide will be the beginning of the.
Very nice. Sentinel. Very nice. Group 10. Everybody vote for Group 10. What do you have over here?
Well, this is our actual interface circuit. This is the PIC that he used for the interface.
Cool.
This right here is the device that we use to synchronize all the badges. We plug each badge into one of these and we hit this button.
Okay.
And it synchronizes them so they're all in sync. So we need that for the time division multiplexing.
And this is an entry keypad?
Yeah, what you do is you enter your numbers, and this light over here lights up, and that says the door is unlocked. And you hit the button, and the door is open, and you walk in.
Also corresponds to the screen.
Yeah, and it says right here, Michelle Immaculate opening the door. And that's
Okay.
that was her. I punched in her code.
Control robotic arm. It was designed for industrial applications to speed up the use of a device for error detection and error correction purposes, so that you could have a fully controlled program that performs all the operations that the robotic arm does, so that you do not any longer require to use the robotic arm directly. You control it from a long distance. Sure.
Okay. It uses 6 standard hub RC servos. One piece of. I made the arm by cutting out a big long 8-foot piece of 1-inch angled aluminum, and also I'm cutting that out, guessing and checking to see where it would fit, mounting the servos, and seeing how that would all come together. I eventually came up with a robot after about 3 months, and we were able to interface it, and this program turned out to work really well with it. The graphics were done with a Caligari QSpace, and they were converted to PCX format, and they were called up in C. And what did you do?
Well, I was in charge of interfacing between the software and the hardware, and I also designed a circuit, an ADC converter, that measures the movement of the joints by a voltage divider. This was done by placing potentiometers in each joint. measuring the voltage that is sent to an ADC, which converts this analog voltage to a digital signal, sent back to the computer, and compared to the digital image and the commands being given to the arm. And this will tell you if it's moving the distance you want it to move, or if it's stopped, or something interfering on the way, or something wrong with the arm.
How cost effective is your application?
Cost effective. We spent about $250 on it, and I don't know how many man hours.
Quite a bit of hours, but this was the first one, so I spent roughly 300 hours on the program. It took a lot of design to get the servos to work well. I already spent about 150 on to get it in these classes. Here and there for a few months, working on that arm, cutting pieces out, fit pieces together, taping the servos down, running cables and wires. Make sure you get a shot of that.
So you guys happy with the overall finish of your project?
Yes.
The design,
It could be improved, but yes.
with more proof servos, this would work perfectly.
Cool. Well, congratulations for finishing your project, guys.
Ryan Hurst.
And what do you guys got here?
Our project is an animatronic figure. It originally was planned to have a puppeteer have an input wear an input mask. The input would then be stored in the computer's memory. Then the puppeteer could go home, and the operator of the computer could then run the program and have the puppet run through routine.
We didn't actually turn in a sheet.
Which would advertise, work in a movie, or provide entertainment. The significance of input mask would mean that one puppeteer could input all the instructions instead of having 3 or 4 puppeteers like they currently do.
This puppet basically has all of your basic components of face and body, neck. We had designed a latex mask last night. We were going to use it today, but unfortunately latex when it dries is really thin. And so when we looked at it this morning, it takes 24 hours to dry also. When we looked at it this morning, it was too thin, and rather than have an interior product, we decided to eliminate that. We have other cosmetic stuff that we're going to put on it, but we figured, well, if you're not going to have a latex mask, there's no sense in putting the other bells and whistles on it yet. Those are still yet to come. Eventually, I want to get this thing to talk and do a lot more other things. So, but that's basically the whole.
It looks like a monkey.
Yeah. Or a gremlin.
Yeah. Or a C6 sea serpent.
What about cost and things like that?
It costs about $300 for all the raw materials to put it together. And
Ryan's got his 2, 8, and 6 here.
the program was done on his computer here.
Assembly code for it.
We went through several circuit designs before settling on this one. Other circuit designs were much larger and more complex, so we ended up with a few surplus chips.
Mike mentioned we're having problems with the torque, even the way that
We were thinking about using analog signals, but we didn't realize that we could use the computer's natural 0 to 5 to operate the servos, which is what they actually operate a square servo wave, square wave. So
A lot of
trial and error.
About 6 to 8 hours on programming and about 25 on the hardware.
That's not bad.
So there's a lot of trial and error here.
Are you guys happy with the way it came out?
Yeah, we're happy with its operation right now. We prefer the way we originally planned it. We had higher expectations, but we just couldn't achieve those in the time allotted.
So small.
Okay. I'm Eric Rudd.
Hey, hi, I'm Art.
To Bynum.
We're all Brett classmates here.
What do you guys got here?
Pinger.
Kind of swing around here a little bit.
Tracking devices to Pinger. What it is our transmitter here. Mobile transmitter. This is what's getting tracked. Got receivers here. Computer interface. Interface to computer. What it does, as you move around with this, you can put this on your car, you can hold it. It makes this a lot smaller, but for all purposes, it's big and bulky. As you move around, you get tracked on a computer screen. I'll show you right now.
notice,
Let me zoom in on that.
as I'm moving
Follow
around,
little dots there.
now just cut it off. And there we go. It's tracked.
So that was where you were moving just now.
That's correct. That's where the transmitter would be moving. Yeah. It took us like worked around 200 hours on it.
200.
Yeah. We basically all tried, you know.
Yeah.
But thank God, you know, today's no more after this. But
Who basically came up with the idea?
We all kind of collaborated on it.
Yeah.
And, we just sat down one day and were thinking of like coming up with something that could locate stolen vehicles, and that's the original idea that we had. Came up with this, we decided to keep it like for this short range applications, like perhaps using it for a household or within just a city block. That way, you can like make it the transmitter the size of a wristwatch, like put it on a child, and keep track of the child like around the house or around the neighborhood, and that way make sure they don't like go down to the pool area and fall in or something.
What about like cost and things like that?
We scrounged up everything out of our lab kits.
yeah, we used just things from our lab kits. That's all.
So it was real cheap then?
Yeah, it was very cheap.
Cost effective?
There you go.
Yeah, very cost effective.
Tuition is very expensive here, so.
So you guys pleased with your overall performance in for the fair today?
Sure are. Thank God it's over with, just about.
Cool. Well, congratulations finishing your project, guys.
Same to you.
Thanks.
You too.
2 stepper motors on a little car inside this track. One stepper is going to be responsible for moving this linear-wise, like back and forth this way. And then there's another stepper which will actually be able to rotate the camera. What we have inside here is like a flat gear, which are actually Lego pieces. And then the stepper has the gear attached to it like this, and that moves along the track this way. What you can see here, I don't know if you can get this on the tape, but this is our software which actually operates the camera and the camera housing. If you go into a manual mode of operation, you actually have 4 options. You can move forward, backward, or rotate the camera right or left. Bring this on down a little way so you can see it a little better. For example, if I go ahead and hit the R, that will rotate the camera clockwise a certain designated distance. So if you hit that, it's going to swing it around, and of course you can see it down here. If you go back in there, you can bring it back around just by hitting the left key, which is counterclockwise. We also have the forward and the backward, and we've actually had some problems with this, just due to the fact that we have a real low torque on those steppers. So if you hit forward, you can see the camera moving along forward, and it actually looks like it's going pretty smooth. And then it'll stop. Then you go back in there, you hit a B for backward key, and that's where it hangs up. You just give it a little tap, and it takes off. So that was one problem we would change.
Okay, then what we have also is I built a junction box for between our computer, and what it does, it takes singing programming, and it sends high pulses on the data lines. We use data pins 2 through 9 to send our data. What we have is our stepper motors use a 12-volt high main pin. So what we needed was negative pulses to step our motors. All we did was send it through inverters, got our negative pins, and that's how we get our steps. It just steps from transistor to transistor and gives you phase steps. Also what we have is the input and the output on the ribbon cable. We also have, within the camera, there's 9 volts and a video receive. And what we did is we used a RCA cable and put it in line into a VCR, ran it to the TV, and this is how you see it.
We also had, besides that manual operation mode, you can go into an automatic operations menu, which would, with one keystroke, you could actually run a series of programs. For example, option 2 on here is just going to rotate that camera around about 315 degrees. It'll pause and then bring it back around. VC is going to rotate right. As we go full, we're going to see these guys over here. As soon as it stops, it echoes a message up here. It says pausing for a few seconds. It'll pause and start swinging back around. And the reason we don't have to rotate 360 degrees, obviously, is because the viewing angle on the camera is about 45 degrees. So we don't have to swing it all the way around.
How long did it take you guys to get all this working? Like, what kind of hours you put into the project?
Well, Mike did the majority of the hardware, and I did the majority of the software. I'd say programming time, I had to kind of relearn C++ a lot, so kind of like you did with your programming in QBasic. I'd say probably about 30 hours of programming at least.
As far as hardware, I've been, ever since the start of the trimester, I've just been putting in an hour, a couple hours here and there. So overall, boy, it's really hard to say.
Yeah.
Right, somewhere in the neighborhood of 50 hours at least, I would say.
How did the costs come out? You guys do fairly well?
Well, as far as the project itself, and we're not counting like my computer, my TV, my VCR.
Yeah, of course.
We did okay. We're probably in about the $200 range. Now, we had a bunch of problems with, we have no tools to build, to cut. I mean, we have metal, we needed metal cutters, we needed drills, drill bits. As far as tools and hardware, we went almost near $600.
Really?
Yeah.
You guys think you might have had the most expensive project here, maybe?
I doubt it.
I don't know.
I think there's a lot more into it as far as...
Yeah. Cool.
I owe Mike a couple $100.
Well, congratulations on getting it all finished and being able to show today.
Our original configuration was what you see before you, which the problem with it was manual inputs. It used the pot to control temperature settings, a Z80 processor sequencer that would input the recipes. Over here we see the obvious problem. By looking at it, the wiring is has no schematic for it, and it's very hard to diagnose any system problems. And then I pass off to my associate Russ.
Hi, how you doing? Our original idea was to replace as much hardware as possible with software. So we were originally going to go with LabVIEW, so that pretty much determined all the hardware we were going to do. It meant that we would need a 4060 x66 computer with at least 60 megabytes of RAM, a multi-IO board in order to be able to interface and monitor all 36 channels required to monitor the entire system. Multiplexer board, which further enhanced the ability to monitor the channels, and 3 8-channel solid-state relays in order to control the gases and the temperatures. The main problem that we came across was that we had to work with existing equipment, so that meant that interfacing between the computer and discrete devices was tricky to a certain extent. What we ended up doing was the main system was controlled by SCR controllers. We hard set the SCR controllers to full power and then use the software using digital output and duty cycle in order to control the temperature using the duty cycle. Of that, we had 5 screens for the software. One of the important considerations was the fact that everything previously was done at the furnace, which is in a clean room, which made it rather cumbersome and awkward for 5 or 6 people. You have to include the process engineer, the quality assurance engineer, the technician, and the furnace operator, of course. So what we've done is we've gone and made it into a software situation, which James will pick up. James, come on down. It's your turn.
Okay. The original concept was for the whole system to be set up on a network. 6 furnaces would be controlled by one computer, and you could have them network into other systems. 6 furnaces. The 4 main parts are the operator allows an operator to select a process, term for it is a recipe, which is just a sequence of steps where either the temperature changes, reactions, or bolts are pushed in or pulled out. They can also monitor the steps for any one of the furnaces. You can look at it on a graphical output and also a digital output. That's a description of the step.
Oh, really?
The next one over here is the technician's panel. The technician panel allows the technician to monitor the maintenance on the system without actually having to be inside the clean room. Most likely they probably would be using it in the clean room still. So, troubleshooting hardware. Next one is over here. This would be the engineering panel. Engineering panel is where they edit, make new recipes. Recipes again are just a series of steps in the process. One of the most difficult things about fusion furnace processing, it periodically has to be profiled, calibrated, and it usually takes an operator all day to do one furnace. So we tried to automate that, and what it does is when you select profile, it uses another program. It's a sequence of, it takes the difference between the actual temperature of the furnace and a probe that you stick on the inside of it measures the actual temperature.
So, is all this an application that you guys have already basically put into use?
All the way up through this, all the way up through the automatic profiling has been used. Automatic profiling still needs some testing and stuff. The way automatic profiling works is there's a probe, a long probe about 5 feet long that you stick inside the furnace, and it's already calibrated. And you put that calibration data into the profiling array here, and what it does is it takes the difference between the actual temperature measured on the inside and the temperature that's running thermocouples on the outside, and it makes an adjustment to it. It goes through a sequence until it's within a parameter set.
What kind of cost were you guys looking at when you were presented with this new application?
The total cost probably is right around probably $10,000. What it costs. Most of it's hardware.
Hardware?
But we're only using about a third of the capacity. Probably run about 3 times.
Are you guys pleased with how it came out thus far?
It came out very well.
Very well.
Yeah. Even our first stab at it, we were not much better than we planned. Our first try out, we were measuring temperatures within 20 degrees accurately.
Really?
And we were holding set point temperatures within 5 degrees. And we were only looking for 2 degrees plus or minus 2 degrees.
Well, that's good. Well, I'd like to congratulate you guys on it.
Teddy bear that does sign language, kind of like a Teddy Ruxpin, but for deaf children. And right now what we have programmed in here is we'll do a 1, 2, 3, here's a 4, a 5, and a 6 is actually the index finger, your pinky finger, and your thumb together. But for time and money, we had to connect the 2 fingers here to one servo. So we can't do a 7 or an 8. We can go in and do a 6 or a 7. We can't do a 6 or a 7. There's an 8. Go into a 9. And the idea was to do letters like A, B, C, D. But in order to do those, like an A is a closed fist, but there's not enough torque pulling down on the servo, so we had to opt for letters or numbers instead. And we have a universal symbol sitting here too.
Oh!
So we've got the frequency controlled servos going by one little pick we've got here. We can plot, of course.
Can you hold it up so I can see it? Oh yeah, okay.
You call it back. He never hit me.
Oh, it's upside down?
Sit up and get it.
Thank you.
Was it really?
And who was that nice guy who just brought that out there?
Yeah, George can explain some more if you'd like.
Oh, well, sure. Tody's cutting across. Hey, wait. Where are you going? You're getting away. Get out of here. Oh, back to the project.
Right, man, look at this, man. Should've got that on your keyboard.
Our fingers are made out of half-inch PVC with joints being made out of tape measure that we cut up. Perfectly good tape measure.
Is it tape measure or tape measurement?
No, tape measure. We have measurements on here. There's about 3 feet of tape measure in the project there. Our total project is about $200. It was under $200 for the total project cost.
Jerry, is it true that you work for ESPN?
Yes, it is. I am a sportscaster with ESPN.
No. Who do we got over here? I heard somebody laughing over here. Who's the clown over here that was laughing at me?
That ain't I.
Who's this clown? What's that say on your shirt there, clown?
We're talking about say nothing.
Are you like an FA?
No. I'm not working.
You're not working? Oh, okay, cool. So what else you guys have to say?
We have nothing more to say. ESPN out. Junior.
What happened to Junior?
Bring your ball in over here.
Junior, come over and be on camera.
Put something on there that will knock off that glare. Put on his hat. Marky poop.
What's that? Junior, tell me about the scheduling and cost constraints of your project.
Well, due to the cost and the time constraint, we had to somewhat come up with an idea that will limit the time that's needed to build this net. So what we came up with was a cost-effective way, which is a PVC pipe, which is very inexpensive.
Well, you guys are at.
Very inexpensive. The cable we used was also inexpensive. It's a 6-part test fishing string. And of course, it came up with an very cost-effective way to make the finger return, which was using tape measure.
What about the program? Can you show me what the program looks like?
Wow, the program. You know what? This guy named Brett Isaac, he really spent a lot of time doing that program. He spent roughly around 100 man hours doing that software.
Can you scroll through it?
Do you want to talk about your program? No. Okay.
As you can see, the program is very detailed.
Nice to meet you.
Only an individual that's knowledgeable with Q-basing will really understand that.
He's the one borrowing your stuff from that tile.
Can you see me still? You looking at the program?
No, I can.
Last week. We're still starting.
Yeah, we're still going.
We did fine.
Well, that's a cool program.
It's like they cut around the toilet.
Well, it looks like you guys did really well.
Well, of course.
I'll bet you're going to win some awards.
We hope. So.
Anybody you guys like to say hi to?
Well, that's funny, but how hard is that? I'd like to say hi to Mr. Halpin.
Mr. He's got some bourbon.
Finally paid off. Yeah, look at that.
Right there. There it is. The fact that they love that. Yeah. Oh, right. Dude. That would happen. There we go.